I hope today, over any other day, you go, I have never thought of math in such a positive way.
I've never thought of math in such a positive way.
I didn't mean to recite that like you're faking it, but whatever. Okay, so we've kind of made the connection a little bit of how a derivative is related to an integral. But I didn't show you why, I didn't explain anything why. We just kind of discussed maybe that relationship, okay? So watch this, please pay attention to this. This is good stuff. Let's say y equals f of x, right? So that's the curve, right? Go back to first semester, y equals f of x. That's the curve. You guys good with that? Yeah. Okay. Let me just say that capital F of x equals the integral from a to x of f of t dt. I'll just give you that equation. Now with that said, look at that for a minute. What is it I'm telling you here? What does this represent? The integral from a to x of f of t dt. What does that mean? That means the area under the curve from a to x, right? You guys okay with that? So in other words, right now, ignore the fact that you kind of know what capital F is or what it means. But just for right now, we are saying that this equation represents the area from a to x under this curve. So all this area. Are you guys good with that? So we're saying that capital F represents that area. So let's see here. That's capital F of x. Now as we look at that, in order to make that area bigger, what would I have to do? How would I make that area bigger? I can't move f of x because that's the f of x, that's given. Make what? Make the interval bigger, right? Now a, in this case, a is a constant, so we can't move a. X is a variable. See that? X is a variable. We can move x. So what would I have to do to make the area bigger? I'd have to move x to the right. You guys okay with that? If I move x to the right, we say the area gets bigger. So real fast, we're saying that capital F is representing the area under the curve. And that all depends on whatever x value I plug in. You guys okay with that? Okay. So if I move x over there, what happened to the area? It got bigger. What would you say, how would you describe the distance from our original x point to our new x point? What expression represents that distance? Maybe plus something. Let's call this, let me put something in here. Let's say that this is x1 and this is x2. Then how big is this? x2 minus x1. If this is x1 and this is x2, then the distance between those two is x2 minus x1. Think back to algebra. What is that thing when you say x2 minus x1? It's not the slope, it's the what? It's the change in x. Okay, so remember way back that the slope of a line is equal to, we do the x2 minus x, sorry, that's wrong. y2 minus y1 over x2 minus x1, right? The other way to express that is what? Delta y over delta x. You guys okay with that? Now let me go a step further. When we're talking about curves and we're actually finding slopes at a point, what did we call these deltas? The lowercase, because that meant a really small change, right? An infinitely small change. So I can rewrite this as maybe delta y over delta x, right? You guys okay with that? Or yeah, the derivative, right? I mean that's what the definition of derivative is. When you make x, the distance between x really small. So this region, how would we describe that region, that yellow region? That's the change in the what? The area. You guys get that? Okay, so this region is the amount the area of the whole thing changed by, right? So I say triangle F, the change in big F, which is the change in the area. What is this distance called? x2 minus x1, but we call it delta x. Okay, so delta big F is how much the area changed by. It's the change in the area. You guys okay with that? Yes. Okay, and then this is delta x. let's just go back to the basic rudimentary area. What did we slice this into to find the area under the curve? Rectangle. So for a minute, let's assume this is a rectangle, because really this is infinitely thin. You got to visualize this as zooming infinitely in, so it's infinitely thin. What is the area of this region then? It's a rectangle, right, in theory? What's the area of a rectangle? We'll say length times width, okay? In this case, what's that area? What's that yellow region's area? Okay, so this is the change in F. That's the area of the yellow region. Equals to, do I know anything? The width is delta x. You guys okay with that?
Yeah.
What's the length? What's the height of that yellow region?
I don't know.
What? It's the function's value, right? How do you figure out the height? You plug in a value to the y. You get what I'm saying?
Yeah.
So in order to figure out if this is a rectangle, to know the height of this, I guess, line, you would just plug in whatever x value you want to use to the function. You guys okay with that? So what expresses the length?
The integral of this?
Just f of x. You guys okay with that? This is the height. This is the width of the rectangle. So we say or the base. The height times the base is equal to the area. You guys okay with that?
Yep.
Okay. I'm going to put it up there in a second, but I like moving my hands around it. It helps me feel like I explained it better. Let's solve for f of x.
Just
Divide by
delta x.
delta x. So we're going to say delta f over delta x equals f of x. I want you to stare at that for 10 seconds.
I've never
So that
seen
would
cross
be
out
a
the
y.
delta
Change.
with
The change with area equals divided by the change.
The area divided by the change of distance.
Wait, how does it equal?
Remember, this big delta means we're changing the area by a big amount, right? And we're changing the width by a big amount. But when we're talking about just moving x over just a little bit, what do we say? We say, we maybe rewrite it like this. df dx.
Is that it?
Are you guys okay with that?
Yeah.
Now go back to first semester. How could I rewrite that? Maybe dy. Look, if I said y equals 3x squared,
Okay.
and I said, what is dy dx? What am I asking you to find? What would the derivative be in this case? 6x. But what's another way of expressing dy dx?
Y prime.
So what's another way of expressing this?
F prime.
Big F prime.
Oh!
What the hell?
So f prime is the area? Well,
No.
not the area, the function.
This is the change in, this is the rate in which the area changes.
The width.
Hold on. You'll see it in a second. Let me put this up there, and then we'll go back over it. So delta f, big change in f, big change in the area, is equal to the height, which is f of x, times the change in the x value. Okay, so we have that. We solve for f of x, or little f of x, and then we rewrote delta f over delta x as the derivative of big F. You guys okay with that? Now, try and understand what that means. Let's go back up to this given equation here, right? What must I do to this side to make it say f prime, or big F prime? What? Okay, so I got f of x. I got f of x equals the integral from a to x of f of t dt.
Take the derivative of.
If I take the derivative of this side, I get big F prime of x, right? But if I take the derivative over here,
You have to take the
I have to take the derivative over here. Now, my notation is going to be a little different because this is Newton, right? I'm going to use Leibniz form over here, d dx of the integral from a to x of f of t dt. You guys see that? I just took the derivative of both sides, right? This is the derivative of f in respect to x. This is the derivative of this function in respect to x. I took the derivative of both sides. You guys okay with that?
Yeah.
Okay. Wait.
Why DDX?
What? Say it again. It just means derivative in respect to x. That's the
It's because you
notation.
don't have a
we
Y.
put. Yeah, there's no y's there, so I can't just say y prime or something. Watch this. Watch this. This is cool. What can I replace f prime with?
F of X.
So this can be rewritten as f of x equals to the derivative in respect to x of the integral from a to x of f of t dt.
It's just turned into math.
Watch what happens here. What does that mean?
That's the line is equal to the.
See f of x?
It's just
See f of t? I'm going to take a step back real fast. This t and t could be anything. These are just placeholders because what's the variable in this function? X is the variable. So the variable's up here. These are just placeholders for now, and you'll see them disappear later on. The variable is really x. So really what we're saying is that f of x is equal to the derivative of the integral of f of x, in a sense. So how do I just get f of x on this side? What happens? The derivative and the integral cross out. They have to disappear, right?
Why?
wait.
Wait,
Hold on. Rewind. State that again.
Let me rewind.
Right. Okay, so
He's like-
watch this. Do you guys agree? Do you guys agree with me that f of x equals f of x?
Yeah.
That's true, right?
Sure.
So f of x equals f of x. I'll just say f of t. In any depending what the variable is, right? You guys okay with that? Okay. F of x equals f of t. In other words, this is equal to this.
Okay.
So that must mean that this operation, the derivative, and this operation, the integral, must do what to each other? Cancel each other out. So watch the logic here. This is great. You ready for this? Wait. Shh.
I didn't think I was gonna come.
The derivative is canceling out the what? Integral. So what would we say about these two operations?
Inverses.
They are inverse functions.
I've never seen math in such a positive way.
Now wait.
You've been waiting all period to say that.
The derivative and the integral are inverse functions. But last semester you learned something else was the inverse of derivative. The derivative and the
So the
antiderivative.
antiderivative is the integral?
Yeah, didn't we learn that? Didn't we say
Hold
that?
on. The derivative is the inverse of the antiderivative. So that must mean the integral
Is that-
and the
I've never
antiderivative
seen math
Holy
in such
crap.
are the same thing.
Yeah, leave this in the video. We're going to be screaming.
Rex, woo! Everybody's getting excited, so I will too, but I don't know why.
No, because I was the one that asked you, is there a way to find antiderivative in the calculator?
Oh, I remember that. I was there.
Okay,
My witness!
there's something even more meaningful than that. Okay, so do you guys kind of see that connection? I'm not asking you to understand it perfectly,
Okay, yeah.
okay? But this does some amazing things for us, okay?
Are we going to write? Hold on, I'm going to write this down.
Wait, so, okay, we're gonna need the
I'm going
notes.
to take this down.
You're gonna need the notes.
Did you say that the semester was all
When are you posting this video?
All right. Well, didn't I just say that?
I know, but that was such a big hint towards like.
All right.
I'm gonna start bringing my own tripod.
What does this mean? It does right now to you, that was the boring part. So wait, there's more. Right? As seen on TV. Okay. Check this out. And we kind of just said this, but I'm going to write it down. The derivative with respect to x of an integral. So when I take the derivative of an integral, I'm just left with the what? What's that called? What's that part called? The integrand. The derivative of the integral is the integrand. Now, there's a little bit of exceptions to that, and we'll get to that in the future. But in general, when I take the derivative of an integral, those are basically inverse functions of themselves, okay? Now, this means, this notation right here, and I kind of have it here. The derivative of the integral from a to x of f t dt equals f of x. What does this mean? A whole lot.
That's it. I was expecting like a nice explanation.
What do we use?
Watch this. Wait a minute. Watch it. We'll get to what this math means.
Okay.
Here's one reason. Okay, we just kind of said it. The integral is an antiderivative, right? Which means Did you know how to take antiderivatives? That means you know how to take integrals. Right? Okay. Hold on. That's the exciting part. Okay? So this allows us to find all those definite integrals that we've been talking about for the last week or so analytically. Okay? Without our calculator. Okay? I'm not gonna dwell on this frame because it's just a bunch of fluff and nonsense. But this is the fun part. Okay? Again, this is the logic for why you can take the why you can take an integral analytically. But watch this. This is fun. Let's say let f be the antiderivative of f. Okay. Do you guys agree with that statement? Based on what I just said, if I take the integral of f, that is equal to the antiderivative of f. Because the integral and the antiderivative are the same thing, right? Okay? So the integral from a to x of f of t dt is equal to capital F of x plus c. Because it's the antiderivative, right? You guys okay with that? Now, I'm gonna have to develop this one a little bit before I put it up there because I want you guys to see it.
Alright.
If I were to replace the x on top with an a, let's just replace it with a b of f of t dt. You'll see what I'm doing. What would that be equal to according to that?
F of D.
It would be capital F of
Plus C.
b plus c. You guys okay with that?
Yeah.
Okay. I'm gonna take a step further. What if I replace it with a? What would that be equal to?
0.
0.
True, but what would it be equal to based on what we just wrote?
F of
Big
A.
as in
Capital F of a
Plus C.
plus c. You guys okay with that?
Okay.
Okay, I wanted to make sure you understood that before I wrote it down. So the integral from a to a of f of t dt is equal to capital F of a plus c. Why did I pick a to go on top instead of some other number?
Because he wanted to be Mr. Buzz.
No, there's a reason. You should know.
magical we're about to learn.
Because you know what the integral from a to a is.
0.
0, right? So 0 equals capital F of a plus c. You guys got that? Now remember, when I take an antiderivative, you have the plus c at the end, right? And you need to have some more information to find the c, right? Okay. This equation right here tells us what c is.
Negative
How do I solve for c?
F.
Subtract f of a. So c equals capital F of a.
Negative.
Negative capital F. Are you guys okay with that part?
Yeah.
So we're going to call that statement 2.
This is like a system.
In a way, it's a systems of equations. So now look at statement 1. Look at statement 2. How can I put them together into one statement?
The interval from
From A
a to x of that is equal to.
Can you just put capital F?
Yeah, this is a pretty easy one. Look, here's c, right?
Yeah, just plug in that.
That's c. So let's just plug that into c there. Okay. So then our final statement we can conclude by putting those together that the integral from a to x of f of t dt is equal to what? Capital F of x minus capital F of a. Think about what capital F means. What does capital F mean in terms of f? The antiderivative. So how could I evaluate the integral? Here's what I have. Let me write this down. Integral from a to x of f of t dt is equal to capital F of x minus capital F of a. Do you know how to analytically, as of this moment, solve that? Solve that.
Yeah.
How?
No, you don't have any
Oh,
numbers.
well, not
It's
analytically.
You don't know how to do it analytically. You know how to type in your calculator, right?
Yeah.
You know how to find some graphs, the area under the curves. But do you know how to do that?
No.
No. You know how to do that?
If that's
What does this say to do?
Take that
Take the antiderivative
and subtract it by the.
and plug in
The high.
x, the upper bound. Take the
Oh.
antiderivative, plug in the lower bound, and then subtract the two. And that is how you take a definite integral.
Yeah, I want to try to.
Okay, we will. Words, okay? We got to make sure we understand this in terms of symbols and words because some people can read symbols and understand what's going on. Some people don't have a clue what that means.
Does the AP test
What does it mean?
know the formats, like the words, the letters? Or just numbers?
This you should know. Okay, so what is it saying to do? It says take the antiderivative of the integrand, right? Take the antiderivative, plug in the upper and lower bounds, and then subtract them. That's all you're doing. Does that make sense?
Yes.
It's actually a very simple process to a very complex thing. You guys okay with that?
We do.
What's that? In order to find the definite integral from a lower bound to an upper bound, you take the antiderivative of the integrand of the inside, plug in the upper bound, plug in the lower bound, and then subtract those two values. Okay. So let's look at one example here. Let's use a function that we know the answer to. Okay? So we've got the integral from 2 to 8 of 1/2 x plus 3 dx. If you didn't know the analytical way, and right now you're not maybe making that connection, how would you go about figuring that out on your own?
Plug it into my calculator.
Without your calculator. You would draw it,
Make a picture.
and you would find
But we know how to do the words. No, we'll use the F.
you find the area that's bounded from 2 to 8, right? What kind of shape are you going to be finding the area of in this case? Either a trapezoid or a triangle. Probably a trapezoid because the y-intercept's not 0 or something like that. Okay? So, but let's do this analytically. What's the first step that I told you to do? Analytically. Take the antiderivative. So, what is the antiderivative of 1/2 x plus 3? What is it? Come on, how do you take antiderivatives?
Squared.
What did you say, Jada? I'm sorry. Fair enough, but how did you do it?
You raise the exponent.
You add a 1 to the power, okay? So you take your coefficient and divide it by your new power, right? So what did you get? 1/4 x squared plus 3x plus c. Okay, so that's the antiderivative. You guys all good with that? Okay, second step. What was the second step?
Plug in the upper and lower bound.
Plug in the upper and lower bounds. So the upper bound is 8, so we're going to plug that in. And simplify that. I got that for you. Don't worry.
Thank you.
So you get 40 plus c. Then what?
Okay, lower bound.
Subtract.
Plug in the lower bound. So we're going to plug in 2. We end up with 7 plus c. And then what do we do?
Minus each other.
Subtract.
Minus each other. What is important to do at this point when you're writing this out?
You have to do the parentheses.
Put parentheses in there because you'll see in a few problems that you're going to make mistakes if you don't put parentheses in. Because when you're talking about integrals, there's a lot of subtraction signs all over the place. So make sure you have parentheses on things, okay? So we're going to say 40 plus c minus 7 plus c. Now notice what happens. The c's cancel out. Do you think that is true all the time? Will the c always cancel out?
No.
In this case, it makes sense. If I plug in a value, I'm going to get something plus c. If I plug in another value and I'm going to get something plus c, when I go to subtract those two things, the c's will turn into 0. This is true because what kind of answer are we looking for when we take a definite integral? We're looking for a number, right? And that number represents what? The area under the curve. So you should get a numeric value. Does that make sense? Okay. Let's do this graphically, though. What do we have? We're doing it graphically. We have a line with a y-intercept of 3 and a slope of 1/2. So we're looking for the integral from 2 to 8. How do I find the area of that guy? So area equals 1/2 of B1 plus B2 times height, right?
Yeet. Well, yeah.
What is base 1 and base 2? Base 1 is, remember the bases are always what in a trapezoid?
Oh, parallel.
Parallel. So this is base 1. How do I figure out what that height is? You got to plug in 2 to the function, or to the integrand. So if I plug in 2, what do I get? Do I get 4? Yeah, 4, okay. So 4 plus, what do we get for base 2? 7, so 8, plug that in. 1 half of 8 is 4 plus 3 is 7. And then what dictates the height? Right, it's this width here, right? Which is 6. 1 half of 11 times 6. Are you ready for this?
It's gonna be
66. Half of that is
lit.
it's amazing. All right, so getting that down there. Does that not just amaze you?
I've never seen math in such a positive way.
You said that already. What?
Because he said that amaze you.
Blowing his mind every time.
Every time. All right, are we good with this?
That's it?
So that means that
Well, we're going to practice it. The reason I chose this function is because we can actually find the area under this curve because it's a line, right? So when we get into more complex functions, you're not going to be able to do it graphically, so you have to have the analytical approach to do it.
Oh, so we can use
No calculators. Can I go on?
does that mean on the quiz?
All right, you guys try these. Okay? Depending.
Mr. Bundy,
Did you find out if our
With your calculator.
said
oh, and then verify.
I know, but I
Okay, guys. What did you get for the first one? 2. Because what's the antiderivative of sine? Negative cosine. Notice this notation. This is an important notation, okay? After you take the antiderivative, you plug in the upper and lower bounds, right? Right? This, what does this little line mean? You guys have seen it in your calculator. What's it mean? It means evaluate. So this notation means negative cosine of x evaluated at pi and 0 and then subtract. That's what that means. Okay, get used to that notation. So that means negative cosine of pi minus negative cosine of 0, and that should have been 2. The next one should have been what? 4? All right. What's the antiderivative of 3 over x? This one is weird because if you tried to move the x up and you got x to the negative 1, you're going to get, when you add it, you get x to the 0 and then divide by, weird, right? You have to think of the function that produces 1 over x as its derivative. Natural log. So the antiderivative is 3 natural log of x. And then plug that in. Don't go, wait, stop. And so I believe it was 6, yes.